So the two types of contraction seen in skeletal muscle. In one, you can see that one end of the muscle is fixed, and the other end you are adding a weight. So this weight or the tension remains constant. This is known as isotonic or iso. Iso means same, tonic means tension. So this is an isotonic contraction. In the other example, you have both ends of the muscle are fixed. Then the length of the muscle cannot change. So iso, same metric length. So this is an isometric contraction. An example is when you lift a weight from the ground. It's an example of isotonic contraction. And when you push the wall will not move. Hence, that is isometric contraction. Different parts of this muscle, for example, you have a contractile element which is the sarcomere, and there is a parallel elastic element and there is a series elastic element. So when muscle contracts, the length is shortened. So you can see how the diamond shape is the contractile element that is shortening. In an isotonic contraction, the contractile element is shortening, and the whole of the green one, that's the green one, the whole muscle becomes shorter. Meanwhile, in the example which is violet one, which is the isometric example, both ends are fixed. Then the contractile element contracts, but because the length is the ends are fixed, the series elastic element expands. That is how a muscle can contract isometrically. Finally, you have some weight, some passive tension acting on the muscle, which is pulling all the elastic elements. There are two ways in which you can put weight. One is the after loading, which means that the weight will act only after the muscle starts contracting. Here in the diagram I have shown a table, and the muscle is pulling a weight, and the weight is kept on the table. Only after the muscle contracts will the weight be lifted from the table, and then only the weight will act on the muscle. This is called after loading, because only after the contraction occurs the load will act on the muscle. And here on the left side you have multiple, I have shown different diagrams in which the weight keeps on increasing, and you can see as the weight increases the contraction force decreases. The force velocity relationship is derived from this after loading. When the weight increases, it becomes impossible at one point the muscle to even lift the weight. This is preloading. In preloading, the weight is acting on the muscle before it starts contracting. So this is an example of passive stretch happening before the muscle even starts contracting. On the left side you can see as the weight increases, the force initially increases, but as the weight increases more and more, the force keeps on decreasing. So in green you have the passive tension, and you are adding more and more weight, and because of the weight the tension inside the muscle increases. In red you have the total tension, that is, once you have kept a weight, then you are stimulating the muscle and it contracts. So that creates a force. This force is the sum of this passive tension plus the force of contraction of the muscle. So if you subtract the total tension from the passive tension, you get what is called active tension. That is the force created by the contraction of the muscle alone. If you take the active tension and you measure it across different lengths of the sarcomere, you will see that there is one length of the sarcomere where you will get a maximum force. That is because it is at that point you have maximum number of cross bridges. If you pull the muscle, that means basically if you add more weight to it, the muscle becomes stretched. If you pull the muscle bigger than this optimum length, then what happens is that the number of cross bridges decreases. On the opposite side, if you push the muscle to make it smaller, what will happen is that the thin filaments will slide over each other, and again that will cover up active sites, and that will also decrease the number of cross bridges. Hence, the force decreases. So there is one length of the sarcomere called the resting length, the optimum length, in which there is maximum number of cross bridges. So it is that point that you have the maximum force. Under physiological conditions, only a certain part of the graph is seen. So here, if in the area marked in blue, that is the region that you see. And when you look at that region, it is seen that the force of contraction is directly proportional to the initial length of the muscle. This is called the Starling's law.